Yeah, so the topic today is unusual behavior, but I'm going to start with something that sort of unifies all elliptic curves over Q. And so let me just start with the baseline definition. So given an elliptic curve E over the rationals with Weierstrass form y squared equals x cubed plus ax plus b, and given a non-zero integer d, we're going to define ED to just be the quadratic twist of E corresponding to D. So this is the elliptic curve whose Weierstrass form is y squared equals x cubed plus d squared ax plus d cubed b. Scaling the a by d squared and the b by d cubed. And so this gives you a curve that geometrically is isomorphic to your original curve, but where that isomorphism doesn't usually descend to an isomorphism over Q. And so in particular, these have very different number theory sort of attached to them. Okay, great. And so the other piece of notation that I want to start with is what I'm going to denote by R2 infinity. So R2 infinity of E is going to be the 2 infinity Selmer corank of E. And I will talk more about what this means later, but for now I just want to focus on the most salient points about the 2 infinity Selmer rank. So the most important facts about this, well, the absolute most important fact about this is that it is an upper bound for the actual rank of the elliptic curve. That's thing one. And then the second fact is that it has the same parity as the analytic rank of the elliptic curve. Okay, so these are both pretty weak. If you assume the Birch-Swinnerton-Dyer conjecture, that would say that the analytic rank equals the rank. If you assume the Shafarevich-Tate conjecture, that would give that this equals this. So all three of these quantities should be the same, but unconditionally we know that the 2 infinity Selmer corank is greater than or equal to the rank, and that the 2 infinity Selmer corank shares the parity of the analytic rank. Okay. So the main theorem I want to talk about, which is quite a journey. So paper from 2017, and then 2 papers from 2022, and then a part of it, which is work in progress, is if we choose any elliptic curve E over Q, then R2 infinity of E twisted by D is equal to 0 for 50% of D. Where by this I mean you consider all the D of magnitude less than H, and then let H go to infinity. This probability approach is 50%. And then R2 infinity of ED is equal to 1 for 50% of D. And finally, R2 infinity UD is greater than or equal to 2. And of course, I didn't actually need to write this down, but you have 50 plus 50, that's 100, leaves 0% for everything else. So the proportion which have higher 2 infinity Selmer corank goes to 0 as you consider more and more twists. Okay, great. And together with these 2 facts, we have, that is the back one. Okay. We just have some quick consequences of this. And these consequences, I've sort of mentioned them in pretty much every talk I've given since 2017. But here's perhaps the most obvious is that if we assume the Birch-Swinnerton-Dyer conjecture, this implies Goldfeld's conjecture. So the Birch-Swinnerton-Dyer conjecture is that the analytic rank equals the rank. And Goldfeld predicts that we have this sort of distribution, but where we consider the analytic ranks rather than the to infinity Selmer co-ranks. And so it's an easy exercise using these two facts to show that if you assume Birch-Swinnerton-Dyer, you get Goldfeld. Unconditionally, we can obviously say that 100% of the twists of any E have a rank less than or equal to 1. And then if we sort of focus in on the case where the analytic rank is even, we have that 100% of the twists with a global root number plus 1, and this is just a synonym for saying that the analytic rank is even. 100% of these have rank 0. Okay.
Excuse me?
Yes.
By BSD, are you just referring to the rank part of the BSD conjecture?
Yeah, you just need.
Not finiteness of Shah and formula.
No, you don't need finiteness of Shah. Maybe I'll just go through this argument really fast. So the key issue is, so the case where the rank, oh no, sorry, I'm talking about Goldfeld. So Goldfeld, yeah, analytic rank is half 0, half 1. And so let's assume BSD is true, and we have these two facts. Then if the to infinity Selmer rank is 0, the rank is at most that, so it can only be 0. That happens at least 50% of the time. But then if the to infinity Selmer co-rank is 1, then the rank is at most 1, but then this has to be odd by the second fact, and so the only odd integer less than or equal to 1 is 1. And so if we assume BSD, then 100% with to infinity Selmer co-rank equal to 1 must also have analytic rank 1. So yeah, that's how you get Goldfeld from BSD without finiteness of Shah. If you assume finiteness of Shah, you get the form of Goldfeld which is for regular rank, which is, I think, a more traditional way of stating Goldfeld, but this is Goldfeld's original conjecture was for analytic rank. Any other questions? You good? No, I'm talking, yeah, sorry, Peter. You looked quizzical. Okay, so just a very simple example of this, or a very specific example, is we can take a look at the elliptic curve x0 15. So this is a modular curve, but it also has genus 1, and we can ask about its quadratic twist family. And the reason one would be inclined to do so is because there's this theorem of Cariani and Newton from yesterday. That says if we have a positive integer d, if this elliptic curve twisted by negative d has rank 0, this is enough to get that every elliptic curve over q adjoin root negative d is modular. Okay. So I don't have too much to say about like what this means, but it is a very significant thing. This is a huge result by Cariani and Newton. Obviously, if we apply my work to the situation, what we can say is that this condition is satisfied for 100% of the E negative D whose global root number is +1, which turns out to be the D equal to 0, 1, 2, 3, 4, 8, or 12 mod 15 that are square free. So 100% of the integers I just said have this rank equal to 0, and so we get modularity over their complex, over the corresponding imaginary quadratic field. Okay, and why this particular example is so important is because it sort of was the impetus for this whole, everything I'm going to talk about today. So in December, I had proved not quite this. I had proved this, but I had missed some stuff. And one of the stuff I missed was this. I hadn't been able to show that Goldfeld was true for this elliptic curve, but then James Newton got in contact with me and said, hey, we have this theorem. Can you tell us anything about what the twists of this look like, what their two infinity Selmer groups look like? And I was like, I'll try, and maybe we can get some partial statement or something like that. But then I like fidgeted with the thing for a week, and I'm like, oh, everything works out. We actually can do things not just for this remaining elliptic curve, but for all of the stragglers. And so the focus of this talk is going to be on the stragglers. Why were these elliptic curves so hard to deal with originally, and how can we deal with them now? And I think it's a sort of standard irony of a talk like this that you see this theorem, it has no conditions, and so the rest of the talk is going to be about very, very special cases of it, because the focus is on what we needed to do to get rid of the final technical conditions. Okay. And so the reason why I missed this curve and some others like it is because they have weird Selmer groups. This twist family, when we consider it at the level of two infinity Selmer coranks, they don't look like unusual Selmer groups. But when we sort of focus in on the finer details, they're very strange, very not normal. And so the start of this talk will be establishing what normal is for Selmer groups. And here the prominent conjectures are due to Bhargava, Kane, Lenstra, Poonen, and Rains. But first, let's set up some notation. So first, a lot of this talk will be dealing with sort of cases of elliptic curves. And the way I sort of split elliptic curves into cases is based on the structure of their two infinity torsion as a Galois module, and more specifically, on their two isogeny graph. So the two isogeny graph of E has vertices given by elliptic curves over Q and edges given by degree 2 isogenies, also defined over Q. So for example, I'll talk about an elliptic curve, and I might say, let's take a look at an elliptic curve that looks like this. And so what this diagram means is that there is a unique 2 isogeny starting from E, and it goes to this elliptic curve E naught. Maybe we can give it a name, call it something like a phi. And the 2 isogeny graph has undirected edges because, of course, for every isogeny, you can consider the dual isogeny, which goes in the other direction. And my usual notation will be to call that phi naught. That's still wrong.
Why is it the isogeny graph of, how does E specifically factor into this?
Okay, yeah, so I was a little bit fast and loose with this. This is going to, the 2 isogeny graph will be the connected component of this monster containing E. Sorry, what was that, Drew?
Are you excluding J invariant 0 in 1728?
No, those curves, those are some of my favorite curves, 1728 in particular. But I only, for these theorems, I'm talking about quadratic twists. So is that sort of the issue you're seeing?
No, I
Oh.
directed is not quite true for those two cases. But don't worry.
Oh no. Okay, I should stop wondering why that's true and probably just keep giving my talk. But yeah. Okay. Okay, I'm just gonna keep thinking. Okay, so yeah, so I'm going to now talk about Selmer groups, but very briefly. So the to infinity Selmer group of E, so for a given elliptic curve Q, is just going to be a certain subgroup of the first cohomology group of the to infinity torsion of E over the absolute Galois group of Q. If you do not understand what this means, that's okay. I really don't have enough time to properly introduce to infinity Selmer groups, and it is pretty much safe to black box this. It won't come up that much in this talk. The way you define this is you just consider the subgroup of this obeying local conditions sort of consistent with your element coming from a rational point. But again, this is not going to be the focus of the talk. Like the reason, yeah, it doesn't really matter what the object is, but we do want to study what its statistics look like. I'm also going to make a bad definition, and I'm sorry about it, but it really makes things a lot easier. It prevents 3 headaches to do things this way. So I'm going to talk about the 2 to the k Selmer group, and this is going to be the intersection of the image of H1 for E2 to the k with the to infinity Selmer group of E. This is non-traditional. This is a small quotient of what is normally known as the 2 to the k Selmer group. But yeah, this one has far better statistics, or it behaves nicer in that way. The Cassels-Tate pairing on it behaves nicer. And there's a third thing that goes well as well, but I forget what it is right now. Similarly, I'm going to talk about the phi isogeny Selmer group of an elliptic curve. So if we have a situation like that, and this is going to be just the intersection of the image of H1 for the kernel of the map var phi, again with the Selmer group of E. And the 2 to the k Selmer rank of E is going to be defined as the dimension as an F2 vector space of 2 to the k minus 1 times the 2 to the k Selmer group of E. So yeah, the 2 to the k Selmer group by itself has exponent dividing 2 to the k. When we multiply it by 2 to the k minus 1, we get something with exponent 2. We take the dimension of that as over F2, and that's our 2 to the k Selmer rank. And this gives us a sequence of invariants for an elliptic curve, which are non-increasing, and which have as their limit the to infinity Selmer rank. Great. All right. And the final definition I need to state what baseline Selmer behavior looks like is just a couple probabilities. So I'm going to use this notation P alt of j given n to denote the probability a random n by n alternating matrix with coefficients in F2 has kernel of rank j. And I'm also going to use a certain limit of this, which I'm going to denote by PPR for P Poonen reigns. And P Poonen reigns of j is going to be the limit as n goes to infinity of 1/2 times P alt of j given 2n plus j. And so what this is trying to do is we're trying to give some sort of limit of this as n goes to infinity. But if we just let n go to infinity in this expression, we run into the trouble that this is 0 unless j and n have the same parity. And because of that, we need to do this funny thing where we restrict to have this be the same parity as this, And then to normalize that, we have to divide by 2. Okay. Okay, and so I'm going to adopt a piece of notation from Savenhagen's talk and talk about the BKLPR philosophy, which is unfalsifiable, as it should be. So suppose E is a thick set of elliptic curves. And we're going to make the set finite, but sort of imagine that we're letting its size go to infinity with some process. So in the original Bhargava, Kane, Lenstra, Poonen, Rains paper, this would be the set of elliptic curves up to a given naive height, and then you would let that height go to infinity. Then what the philosophy says is we're going to take E at random, so uniformly at random from the set E. Then for any non-increasing sequence of ranks indexed by the powers of 2, the probability that the 2 to the k Selmer rank of E is equal to R2 to the k for k greater than or equal to 1 is equal to PPR of R2. So the 2 Selmer rank has behavior as given by Poonen and Rains. And then for the higher probabilities, we just have P alt. So the P alt of R4 given R2, P alt of R8 given R4, and then et cetera. So we have this sort of Markov behavior for how the 2 to the k Selmer ranks behave. Oh my goodness. Okay. And so the next thing I want to explain is why, is sort of ignoring this, why do these terms show up, in my view? And this has to do with one of the 2 structures that are really important to consider when we're talking about how Selmer groups are distributed. One of the 2 pieces of structure that sort of must be considered if you want to come up with an accurate guess of how things behave. I'll get to the second piece of structure later. But this first structure is the Castle-State pairing. Okay. And so how the Castle-State pairing works is if we're given an elliptic curve E, and if we're given an integer k greater than or equal to 1, the Castle-State pairing associated to E at level k is going to be an alternating pairing on the 2 to the k Selmer group multiplied by 2 to the k minus 1. So we start with the 2 to the k Selmer group, and then we multiply it by 2 to the k minus 1 to get a vector space. And just to save sort of time, I'm calling this an alternating power. And so this pairing has images in half of Z mod Z, or Z mod 2, or whatever. And its really important property is that its kernel is 2 to the k cell 2 to the k plus 1. So the kernel of this pairing has dimension equal to R2 to the k plus 1. And so the heuristic that I really recommend for understanding how higher Selmer ranks behave is that this pairing is random. So it can be any alternating pairing, and so which pairing it is uniformly chosen at random. And if that's true, then yes, the exact statistics we see from the BK LPR are what come out. Okay. Now, before I move on from the Castle-State pairing, I do want to mention one other special fact about this. And the special fact concerns if we have these two elliptic curves joined by a 2 isogeny. And here I'm using hollow vertices to indicate that maybe these have other edges going elsewhere, but I don't care about that right now. All I care about is this one edge. So we have these isogynous curves, and we can talk about the isogeny going that way and the isogeny going that way. Okay, and we can consider what happens when we look at the restriction of the Castle-State pairing, let's say at level 1. And instead of looking at the full 2-summer group, let's look at a smaller piece of it. Let's look at it restricted to the var phi summer group, or sorry, the phi summer group. And this is again an alternating pairing on some subdomain of the 2-summer group. And the thing I want to mention about this is that when we consider the kernel here, this restriction has kernel equal to var phi naught of the 2-summer group of E naught. Okay, which will be relevant later. And how I like to think about this is this Castle-State pairing at level K measures the obstruction to lifting a 2 to the K Selmer element to the 2 to the K plus 1 Selmer group. In the case where we have this 2 isogeny, we can actually split this division by 2 process in half. So rather than lifting under the multiplication by 2, we're lifting under sort of halfway, so under this phi naught. Yeah. So somehow this measures less, but sometimes that's useful for us. Okay. Great. Okay, and so this is the BK-LPR philosophy, and it's sort of what we expect if there's no other structure that gets in the way. In this paper, they talked about sort of thick families, but this philosophy holds true for some smaller families, for some twist families. And so here's a theorem of mine. Suppose we're in either the case where E has 2 isogeny Selmer group looking like this, so with 4 vertices, or that we have E just 1 point. So in this case, we have full rational 2 torsion, but none of the elliptic curves isogynous to E have full rational 2 torsion. That's one case. In the other case, we have an elliptic curve with no rational 2 torsion at all. Okay, then in either of these cases, the twist family of E obeys the BK-LPR philosophy. Okay. So what this means, is the behavior we expect from all elliptic curves is seen in these sort of miniature families. Okay. And I actually want to mention a little bit about the proof of this, but in a very hand-wavy way. So it's a story of 2 machines. And the first machine takes as input a nice twist subfamilies And specifically, the thing that makes them nice is that they have nice two Selmer groups. And I'm going to be just super vague about this, but yeah, you need a lot of control on what goes into this machine. These twist subfamilies need to be really small. These two Selmer groups need to be really just perfectly perfect. But if you have all this super well set up, machine one will give you equidistribution results for the Castle state pairing. And once you have equidistribution results for the Castle state pairing, again, that's exactly enough to get these probabilities for forever and ever. So in fixed families with nice two Selmer groups, we get these sort of heuristics for the higher Selmer ranks. But that's only half the story. That explains what we do once we have those nice two Selmer groups. And so in order to do that, or in order to get to that point, we need a second machine. And this machine is responsible for the two Selmer groups. And so what you input to it in these cases is just an elliptic curve in either of these forms. Okay. And somehow this machine is not as complicated as this machine. I think this is sort of the more breakthrough-y part of my work. Again, I'm not going to talk too much about it. Whereas this machine, there was actually already a version of this available to me. When I was just considering this case, I was able to, instead of making my own machine, work on using the machine developed by Kane and Swinnerton Dyer, with that in turn being based on work of Heath Brown. But then in order to handle this case, I had to actually sort of go back through that and develop a machine from scratch. Okay. And the reason I've drawn it like this is this sort of two-machine picture will keep being relevant. But what will happen is this machine 2 is not very picky. You can put whatever you want into it. Any sort of Galois module, you can talk about what happens to the two Selmer groups of its quadratic twists. The problem is, unless you have an elliptic curve like this or like this, when you do that, the stuff that comes out is not quite nice enough for machine 1. And so that's where you run into problems. And so a lot of what I'll talk about for the rest of the talk is what we need to do to get around these sorts of problems. And in order to talk about that, I need to talk about what can go wrong in the two Selmer group, which brings me to the second piece of structure that's super relevant. Any questions at this point? Okay. So the first piece of structure that was really, really important was the Castle state pairing. And the second piece of structure is for Tamagawa ratios. And the general phenomena that Tamagawa ratios are sort of expressing are the effects of the Greenberg-Wiles formula, relating the size of a Selmer group to the size of its dual. But we're going to sort of focus in on the relevant case for our work. So this is a piece of notation. Given a positive, let's say non-zero integers n and d naught, we're going to take s n d naught, and this is going to be the square-free integers such that d naught is positive and d naught is a square for p dividing d. No, wait, sorry, the p dividing n. So we're just looking for square-free integers that have the same p-adic behavior. Then the Tamagawa ratio proposition is suppose we have a partial two isogeny graph that looks like this. So we have an elliptic curve E, isogynous to an elliptic curve E naught, with a isogeny phi going one way and an isogeny phi naught going the other way. So we're going to fix this picture, and we're also going to fix a D naught. Then there is an integer u, depending on just the isogeny phi and on D naught, such that when we take the difference of the var phi Selmer group of E twisted by D, and the phi naught Selmer group of E naught twisted by D, this is going to equal this constant u plus the sum over the primes dividing D. I really wish I went to a new board for this, so sorry it's getting a little small here. But the dimension of the set of invariants of E2, or E naught 2, under GP, minus the same for E. Okay. And this is going to hold for D inside of the set Sn, where n is going to be twice the conductor of E. Yeesh, this was bad. Okay, but that is in fact the result. So we have this relation between the var phi Selmer group and the var phi naught Selmer group, which holds throughout this sort of twist subfamily. And then the possible summands here tell us a lot about how the two Selmer group is going to behave. So as an example, we can take a look at an isogeny tree that looks like this. So we have an elliptic curve with partial two torsion that's isogynous to an elliptic curve with full two torsion. And then it doesn't really matter what happens over here. But we have E and E naught. Let's call this isogeny var phi. Let's call this var phi naught. Okay. And so in this case, let's take a look at what possible summands could be here if we vary our twist D of this elliptic curve. And then the summands, well, either, first off, this dimension is always 2, because this curve has full rational 2 torsion. So we have the maximal 2 for this first term. And then the second term can either be 1 or 2, depending on whether P splits in the splitting field of E, the 2 torsion of E. So in this case, the summands are either 2 minus 1 or 1 minus 1. So they're either 1 or 0. And we expect them to be half of this and half of this, approximately. And so what that means is that as D gets more and more prime divisors, we expect the var phi Selmer group of E to grow sort of uncontrollably. What we find is that Zilf phi ED is huge. Again, as D sort of goes to infinity, probabilistically. And this is counterbalancing when we sort of consider what's happening at phi naught. The fact that this is huge means that usually the phi naught Selmer group of E twisted by D is 0. So both of these happen 100% of the time because these summands just grow so fast, or because these summands are always non-negative and often positive. And the fact that this is 0 100% of the time is why in this picture, this elliptic curve was safe. We got just sort of a normal behavior for the two Selmer group because the isogeny components of the Selmer group for E don't really affect anything. Okay, so that's one example. And now the next example is where we have an elliptic curve that's isogynous to one other elliptic curve, which only has partial rational two torsion. And so in this case, we actually need to divide further. This is not enough to really understand how the Selmer groups behave. What we need to, in fact, split by is whether the splitting field for the two torsion of E is equal to the splitting field for the two torsion of E naught. So let's consider the case that these are different. But maybe I've run out of space on this particular board, so yeah. Okay. Ugh. Next board is getting the eraser, I think. This is very clean though. Ah, beautiful. Almost there. Oh no. Okay, good enough. Okay, so yeah, the first case we're considering is the case where these splitting fields are different. So we have E and E naught, and I'm going to just put a does not equal to indicate that they have different splitting fields. Okay, so what happens in this case? In this case, the summands that go in here can take one of three different forms. About a quarter of the time, they'll be +1. About half the time, they'll be 0, where either this is 1 and this is 1, or this is 2 and this is 2. And the remaining time will be -1. And so, yeah. The summands are +1, -1, or 0. And maybe that sounds like they're balanced. In fact, they really are balanced. It's sort of equally likely to go positive or go negative. But you should think of this as sort of a random walk. It starts out at 0, but then as the number of prime divisors increases, the random walk just sort of meanders away from 0, sort of at the rate of about square root the number of steps. And so what that means in practice is that when we consider the twists, what we find is that 50% of twists have a var-phi-Selmer group of E twisted by D huge, and then 50% have phi naught Selmer group huge for E naught. Depending on whether this thing goes really positive or really negative. And the case where it sort of stays near 0 happens 0% of the time as we make things go off to infinity. But this particular, yes?
But is this huge like the square root of that huge?
It is, yes, exactly. This goes to, so yeah, Jordan's absolutely right. This is the slowest process I have, the hugeness of this. the number of twists for which these are actually balanced is like 1 over root log h, if we consider all the twists up to h. So that is a small denominator, but it does in fact go to infinity. 0%, do not care, doesn't matter. Yeah, as opposed to this where it's 1 over log h. Okay, any other questions about this? Yeah.
We have the one which is huge, the other one will generally be 0.
Yeah, this is absolutely right. And Zev is actually mentioning more or less his own result with, no, it is though.
Not the tiny part on the other one.
That's not part of King-Klagsford? I thought it was. Okay. No, so what Zev...
Kind of repeat the question because I can't really get the microphone.
Oh yeah, I probably should do this anyway because of the recording. What Zev is mentioning is, I drew this seesaw, but in general, if this is huge, if one of the Selmer groups is huge, the other Selmer group is going to be 0. And the heuristic here is that, well, the reason we get this sort of behavior at all is like the sort of behavior that this is representing is that we have too large of an ambient space with too few local conditions. And so when we have those local conditions, they just don't cut up. The part that's left is enormous. And so how you can think about that heuristically is you just choose sort of a large space over F2 and then pick some small number of conditions that these things satisfy at random. Okay, I am sort of confusing myself even by explaining this heuristic, so let me go ahead and okay, no, I'll come back to this in just a few minutes, but yeah, in general, if this is huge, this is typically 0. And that happens in this case as well. Okay. Before I get to what I was talking about before very obliquely, let me mention a little bit more about this case, because it's a first, and it's a good example of how we can sort of adapt the two-machine approach to actually prove Goldfeld's conjecture. Okay, so the input to the machine is just this sort of picture. And we put it into machine 2. And what we find is that half the time, the two Selmer groups of E are going to be nice. So in particular, this niceness condition amounts to asking that self-var phi of ED is equal to 0. And we can sort of look at the twists where this condition is satisfied as a subfamily of twists. That's a nice family where the two Selmer groups are nice. So we plop them into machine 1. And what we get is we get Goldfeld, or Goldfeld for R2 infinity, on this subfamily. Okay, so yeah, if we just apply machine 1 to the output of machine 1 or machine 2 directly, what we find is that among the elliptic curves where the var phi Selmer group is equal to 0, the two infinity Selmer groups sort of behave as we expect. And that tells us, yeah, that we have this 50-50-0 distribution for the two infinity Selmer group, Selmer ranks, at the end of the day. But that's only half the story, right? We somehow need to deal with the case where this isn't true. But in the case where this isn't true, we can actually still apply machine 1. But whereas for these curves we looked at ED, let's instead look at E not D. So the var phi Selmer groups in this branch are going off to infinity, but the var phi not Selmer groups for E not D are still nicely behaved. So we put them into machine 1, and then we get Goldfeld on this family. Again, for R2 infinity Selmer ranks. Okay, but now we have these two subfamilies that together make the whole family, so we smush them together, and that's actually how we prove Goldfeld in this case. Okay. Yeah, so that's how I handled this, and this was the last sort of curve I handled back in 2022. Everything else I'm going to talk about is going to be work in progress, starting with the contrasting curve in this case, where we have E and E naught. Okay, and so in this case, the summands are actually always 0. In this expression. And so the relationship between the varphy and varphy not Selmer group is expressed in just this term. And so now we're left asking, well, how does the varphy Selmer group behave in this case? And it behaves like the kernel not of a random alternating matrix, but just of a regular matrix without any alternating condition. So I'm going to take PUR to be the probability in n by n matrix, or sorry, let me say n by n plus r matrix, r u matrix over F2 has kernel dimension j as n tends to infinity. Okay, so we have this big matrix with slightly more or less columns than rows, and we're taking a look at their kernels. What did I say? R is what goes into here, so it's just some non-negative integer. Oh, shoot. Thank you very much. It's slightly different than before because, I don't know. Anyhow, what we find yeah. Here's the theorem. Given this picture where we have equal splitting fields of E and E naught with varphy going one way, the probability that a random twist of E, dim varphy Selmer group of ED, the probability that this is equal to a given integer R phi is equal to Pu of R phi, where we're taking U to be U of varphy D naught, and where D is varying inside of S, twice the conductor of E, D naught. Yeah. So it looks like a kernel of a random matrix. Again, with this difference in columns and rows determined by some constant depending on this starting D naught. And this is sort of what we expect. So this is a pretty normal looking isogeny Selmer group. But now we're in sort of a, how do we go from this to understanding the two Selmer groups? Is the remaining thing to understand. And the relevant piece of information to consider is the following exact sequence. So we have the varphy Selmer group of E twisted by D, mapping into the two Selmer group of E twisted by D. And then the co-kernel of this map is equal to a varphy of the two Selmer group of E twisted by D. So this is a decomposition of this. And what you should do is you should recognize that this has shown up before. when I mentioned the castle-state pairing, this term showed up as the kernel of the restriction of the castle-state pairing at level 1. Again, restricted to the var-phi-naught-Selmer group. So yeah, E0 1. Okay, so that's how this particular thing has shown up. And so what does this say sort of heuristically? Well, heuristically, this is a random pairing. And so if we want to account for a 2 Selmer rank, so we're saying the probability that both of these are hold dim to R2 of E twisted by D is equal to R2. The result is going to be PU R phi, and then the probability that this kernel, which has size R2 minus R phi, is the kernel of a random pairing on this, on this, and the dimension of this is similar to R phi, but let me just remove that. But where we need to adjust by this factor U, because what needs to go in here is the phi-naught Selmer rank rather than the phi Selmer rank, and that's this. And so this describes how the 2 Selmer groups behave in this family. Okay, and so yay, we now have a weird piece of 2 Selmer behavior. This is very unusual. The isogeny is really sort of mucking up the picture of what the 2 Selmer group looks like. And so how do we get around this when we look at the higher Selmer groups? And I'm just going to draw another diagram with some machines. So when we just put in ED into machine 2, it actually works okay. We do in fact get an equidistribution statement of the castle-state pairing, but with a blind spot. When we actually go through the method, this machine has a blind spot when we look at the restriction of the pairing to the portion coming from the isogeny Selmer groups. So we don't know how the matrices behave on this bit, but otherwise we are doing pretty well. But now the trick is exactly the same. We just look at what's happening over at the isogenous curve. We put it into the machine, and we again get an equidistribution stop with a blind spot for the var-phi-naught Selmer part. Okay. And now the piece of good news, the thing that makes this all work out, is that these 2 blind spots don't overlap at all. So if we smush these together in a sort of natural way, we're able to figure out all the higher Selmer distributions. Unfortunately, I'm out of time, but the last thing I wanted to mention was that this blind spot actually is important. Like, the reason this machine has this blind spot is otherwise you would be able to prove that for any elliptic curve, the probability of a given 4 Selmer rank given the 2 Selmer rank is always P alt, and that turns out not to be the case. So it's good that it has this blind spot, because otherwise the machine would just be wrong. But yeah, that's my time, so sorry for going a little late, but thank you.